Okay, good morning, everybody. This is the basic concepts of chapter 17, the chapter on equilibrium. First thing we want to do is to define equilibrium. So if you look at the reaction of A going to B, B going back to A, first of all, that reversible arrow indicates equilibrium, meaning we have reactant going to product, product going back to reactant. So the Kf on the top of the forward arrow indicates the forward rate constant from reactant to product, and Kr refers to the reverse rate constant. Now, equilibrium is defined or established when one condition is met. That condition is that the rate of forward reaction must be equal to the rate of reverse reaction. Or, in other words, from the rate law, we can write Kf times the concentration of A must be equal to Kr times the concentration of B. Remember, this is from the previous chapter, chapter 16, the kinetics of chemical reactions. Now, that equation, Kf times A equal to Kr times B, can be rearranged into equation 1. In other words, what I'm doing now, I'm just rearranging that equation to write a Kc expression. The Kc, which is called the equilibrium constant, and it is very important for us to be able to relate to this as we proceed through the chapter, is defined to be the product concentration at equilibrium, in this case B, divided by the reactant concentration at equilibrium again. So basically Kc, which is called the equilibrium constant, is the ratio of the product and reactant concentrations at equilibrium. Now, it's important to note that the B and A appearing in equation 1, they both refer to concentrations of reactant and products at the point of equilibrium. If these concentrations are not equilibrium concentrations, then that is not defined as Kc. So Kc has a very specific meaning. First of all, we have to know what Kc refers to. Kc refers to the equilibrium constant, and also B and A in that equation refers to the concentrations of A and B at equilibrium, respectively. Now let's go to the second page, page 2. For a more general reaction where we have stoichiometric coefficients, A plus B going to C plus D, where lowercase a, b, c, and d refer to stoichiometric coefficients, where they can be numbers like 2, 3, 4, whatever. The expression for Kc includes now, as is reflected by equation 2, these stoichiometric coefficients. So the stoichiometric coefficients become powers of those concentrations. So therefore the Kc is now C to the C, D to the D divided by A to the A, B to the B. But it still remains, it keeps the same format, that product concentration divided by the reactant concentration. But in this case, now we just have to raise them to the proper stoichiometric coefficients. And don't forget that this is not C plus D, it's C times D, or A times B. So there is this misconception that sometimes when you write Kc, you have to add them. No, you multiply the concentrations always, okay? Now, an important note about the notation. First of all, I explained in the beginning that this reversible arrow indicates equilibrium. So if we have a reversible arrow, that basically means we are operating under equilibrium conditions. The second important note about the notation is that, again, I already mentioned this, that the concentrations, all these concentrations in the Kc expression refer to the concentrations at the point of equilibrium. If these are not equilibrium concentrations, then that is not Kc. It is actually something else which we refer to as the reaction quotient, which will appear shortly in the next slide. Okay. Now, if we have reactants and products taking place, or I should say reactions taking place in the gas phase, which is a very common thing in chemistry, then, so everything is in the gas phase, as you can see in this reaction, then instead of writing Kc, we have to write another expression called Kp, where Kp is called the partial pressure equilibrium constant. So the Kp now, instead of writing concentration, we have to write the partial pressures of these components. Okay, so it's going to be the pressure of C to the C, the pressure of D to the D, divided by the pressure of A to the A, and pressure of B to the B. So again, lowercase refers to stoichiometric coefficients, and capital letters refer to reactants and products. P refers to partial pressure, and Kp is called the partial pressure equilibrium constant. And now, another important thing is that Kp and Kc are related through this equation, equation 4. In other words, if you know Kc, you should be able, in theory, to derive Kp from it using this equation. So Kp is actually related to Kc through this equation. So Kp is equal to Kc times RT to the delta N. In the next slide, we talk about those constants appearing in the equation 4. So in equation 4, R is called the universal gas constant, which you're already familiar with. T is called the Kelvin temperature. Again, you know what that is. If you have it in degrees Celsius, you have to add 273 to it to make it into Kelvin. And delta N, now this is a new thing. You haven't seen this thing before. Delta N is the difference, okay? It's the difference between the moles of gaseous products and reactants. For example, I have given an example here to calculate delta N. 2A plus 3B going to 4C plus 5D. Delta N is going to be the sum of the number of moles of product, 4 plus 5, minus the sum of the number of moles of reactant, 2 plus 3. So therefore, delta N for that reaction is 4. Remember, it has to be a gas reaction where you can find delta N. If it's not a gas reaction, or a reaction that is not taking place in the gas phase, then delta N is meaningless. Delta N only applies to gaseous reactions. Now, the new topic which I'm using now is I'm using a red marker to indicate a new section. Modifying equilibrium constant. There are 3 rules we have to follow. Rule number 1, when we reverse a reaction, the equilibrium constant for the new reaction is the inverse of the old one. So for example, if A goes to B has a Kc equal to 10, and then when we reverse the reaction, B going to A, Kc becomes, the new equilibrium constant becomes the inverse of the old equilibrium constant. Now let's get to rule number 2. Rule number 2 is about multiplying a reaction by a factor, and that is basically spelled out here. When we multiply a reaction by a constant factor, the new equilibrium constant is raised to the power of the old equilibrium constant. So for example, if I'm using the same example. If A goes to B has a Kc equal to 10, and then we multiply through by a factor of 2, so now the new reaction is 2A going to 2B. The Kc for this new one is going to be the Kc for the old one raised to that constant factor, which is 2. Rule number 3, when we add chemical reactions to obtain a net reaction or a sum reaction, the equilibrium constant for the net reaction is going to be the product of the individual reactions. So, for example, if A goes to B has a K equal to 10, B plus C, another reaction, goes to D, has a K equal to 20. Now, when we add these two reactions, meaning that we cancel out the identical components on opposite side, then A plus C on this side remains, and D remains on the other side. So that is called the net reaction, A plus C going to D. That net, which I've indicated here, net reaction, so the net reaction has a K, which is not the sum of the individual K, but instead the product of the individual Ks, which is 10 times 20. So when you add reactions to get a net reaction, then the new reaction has a K that is a product of the old Ks. Now, I believe you have this new section in your text as well, comparing Q and K to determine reaction direction. First of all, we have to define K. K is called reaction quotient. Now, for a general reaction like this, Q is defined to be C to the C, D to the D, A to the A, B to the B. Now, this equation, as I've pointed out here at the bottom, is very similar to the Kc expression with one difference. These concentrations appearing in the Q, or the reaction quotient, are not the equilibrium constant. So in other words, this A refers to the concentration of A, not at equilibrium. Because if it's at equilibrium, then this becomes K, not Q. So reaction quotient, as the name implies, is just a quotient. It's just the ratio of the product concentration over the reactant concentration, where those concentrations are not necessarily the equilibrium concentrations. Now, so I've explained that over here at the bottom of the page. And it's important to note that there's a difference between Q and K. Now, how do we use this information to determine in which direction will the reaction go? To determine the direction in which a reaction is more likely to proceed, and by that I mean which side of the chemical reaction is more favored, we have to compare Q and K. Now, if the numerical magnitude of Q is less than numerical magnitude of K, then the forward direction is favored. And by forward direction, I mean from reactant to product. If Q, or the reaction quotient, is greater than K, then the reverse direction, and by that I mean product going to reactant, is favored. And if K happens to be equal to Kc, then there is no net direction that is favored, and the reaction remains at the point of equilibrium. Okay, so this basically covers the first few sections in the book. The next section we're going to cover later on for a different session is going to be about the important concept of equilibrium calculation, or how to use the ICE table. Okay? Well, have a great day, everybody. I'll see you next classroom.